what makes up nothing? What makes up the empty space that is outside of the universe, outside of our Earth, and fills most of what we know, right? Everything lives under this construct called space, and what makes of it. For centuries, this problem has been confusing and confronting physicists to develop more and more satisfying theories of reality. After all, how can we define the intangible space that we live in after we take out all the air, the furniture, right? All the things we call mass, after we take them out, how can we define it? Is there simply nothing, or is there something? And that relates to a concept called a vacuum. How can we define it? How can we define a vacuum? And on the surface, this type of question is extremely paradoxical and self-contradicting. Isn't nothing just made of nothing? Or is it? The straightforward answer to this question is we don't know yet. At least not entirely. There have been many efforts made to describe reality in a satisfying way, like how black holes evolve, how they explode, and how light moves. And these are all theories to explain how these complicated matters evolve and how they work, of course. But when we turn back and ask ourselves the very simple question, well, what is nothing? We seemingly cannot answer that. And I am not a physicist, but today I'll be sharing with you not the complexities I found from mathematical equations, but from what I had found by retracing the footsteps of our understanding of the vacuum. And by looking at how people came up with new theories, new ideas, by looking at how they confronted themselves against nature's paradoxes, we can perhaps all gain some insight on how sometimes not knowing something itself contains great value. All right, let's begin. So our journey begins quite recently compared to the vast thousands of years of human development to the discovery of a strange wave phenomenon. Everything is made of waves, or a lot of things, right? Sound waves, water waves, guitar string waves, a lot of things, you name it, right? And all of these waves, they must pass through a medium. Water waves through water, guitar string waves through the strings, and it's really just middle school knowledge. But by the turn of the 19th century, there came an astonishing discovery: light. That's really surrounding us everywhere, right? This thing that we call light, something we once thought of was a particle, was shown to behave like waves. Now, at the time, it was the prevalent idea that everything wave-like should travel in a medium, right? Just as I've said. And like how water waves must pass through a water, it's our intuitive understanding of the world that guides us into thinking, well, there has to be a medium for light as well. But we also know that light can pass through the vacuum. And isn't the vacuum just pretty much made of nothing? And this question that started this talk was presented to physicists at the time. So people had to come up with an explanation of it. People had to solve this dilemma. And that was when physicist James Clerk Maxwell began propagating this famous concept called the luminiferous ether. And imagine, and the ether theory is quite simple, actually. It's just following the medium idea, that everything has to live inside of a medium. And what Maxwell thought of was that there's this ether thing that everything lies into, right? There's this substance. And one of the things he predicted that this theory will have some experimental tests that can really see if this theory works or not is that it's something called the ether wind. And so imagine, right, this is the ether, and we all live in it, and we can't feel it, we can touch it, but it's still, it's not moving anywhere, it's not going anywhere, it's just there. And us people living on the Earth, right, Earth is rotating around, we're not around, but inside this thing. And so if this entire ether thing is still unmoving, then on Earth, on a rotating object, we will see the ether actually moving, right? So Then Maxwell predicted that there will be all sorts of effects, right, such as drag of objects, so that they might move slower through space. But sadly, there was no experimental evidence supporting this idea. And what did Maxwell and his companions do? Well, they said, well, if this entire Steele theory of ether didn't work, let's just make the ether theory move. And they changed the theory so that when our Earth moves and rotates, the ether rotates along with it. And then that sprouted even more experimental predictions, but experiments failed and it didn't match up with their predictions once more, and again and again. Maxwell was pretty stubborn on this, and he and a few companions decided to stick with this idea and change it for a lot of more rounds, to an extent where it became really complicated that it started predicting all sorts of supernatural things, and it's really untestable anymore. That was when Einstein's theory of special relativity jumped in. Einstein basically said, well, let's screw the entire ether theory. Let's just assume there's no medium whatsoever the light can pass through. Let's just say the light can just pass through nothing. Okay, that's a ridiculous idea, but let's just say that. And in fact, he invented, or he used this mathematical formulation, and this is called special relativity, of course, and he explained everything that Maxwell had a hard time with using basically a transition or a correction in space and time itself. To put it in other words, space and time is changed in moving objects. And in this diagram, you can see on the far left is an unmoving sphere that is moving at the speed of 0 meters per second. And on the far right, this object is moving very close to the speed of light at 0.9 c, which is 90% of the speed of light. And when this object moves faster and faster, when we're standing still and we're looking at it, it becomes shorter. The length gets contracted. And that's an experimental fact we know. We knew when Maxwell was proposing his ether theory, and we couldn't explain it. But Einstein's theory said that this is basically because in the moving frame, imagine I am the sphere. My concept, my perception of space and time will differ greatly than yours. And that means that the length we see, the time we see, will all be changed. And Einstein's theory was an instant success. It fitted with all experimental predictions. It was perfect, but only to the extent that it seemed a little bit too perfect. Because what about the light theory that you just excluded from, right? What about the ridiculous idea that light can just travel through a sea of nothingness and magically pass energy? Isn't that weird how there don't need to be a medium for this thing, this wave called light moves through, right? This is ridiculous. And when Einstein first proposed this theory, his entire thing wasn't successful and he wasn't popular because all of the other physicists thought this was only a temporary theory before the actual thing, before the actual medium theory gets worked out. After all, our intuition permits nothing else but a medium. And I'll come back to this idea later. Eventually, we move forward to the 20th century, where we discover that things on the smallest scale, on a scale smaller than all our senses can feel, hear, see, things don't behave like the way they do in large scales, like we see the world every day. Things don't behave normally. And that was the discovery of quantum mechanics. And there are just two basic principles I want to share with you today that gives you an idea of how this entire subject works, or what this thing says. First is the energy is discrete. There's no continuous energies. So each thing, there can only be made of 1 + 1 + 1 packs of energy. There is no continuous amounts of energy. The second thing is that this is also called the uncertainty principle, and that is that we cannot measure both the position and the momentum to 100% accuracy. And that sounds a little bit confusing, but it really means I cannot stand still here in principle. Even though I think I'm standing still, I am not. And my position can vary greatly. And that is very counterintuitive. How can we understand this? The real fun starts when you apply quantum mechanics, all these principles, to things like light. And we once more discover something even stranger, that light, again, behaved like particles. So what the hell is that, right? This light thing, it was a particle, it became a wave, and then it ended up as a particle again. That is very confusing, and we face the same position as physicists perhaps in the 19th century face again, right? At the time, it was, how can light pass through a sea of nothingness? Now it's, how can light be both a particle and a wave? So you see how progress is made. It's when there are paradoxes, things that we can't seemingly solve. It's self-contradictory. But these are good because it's indicators of progress. And that is when a theory tried to combine wave theories, which is really what we first thought light was, and quantum mechanics, which is discrete amounts of energy. So continuous waves and discrete energies. And yeah, that is called quantum field theory. So behind me here is a simulation of what we now think constitutes the vacuum. And what you are seeing now is that in this tiny, tiny space, it's probably smaller than a few nanometers, it's really, really small. There's these quark and gluon waves. These are waves that fluctuate in and out of existence very rapidly. And this is just a very exaggerated time scale. The actual thing probably moves in and out, fluctuate, bubble around much faster than this. And so this seems unrealistic because we don't see vacuum as this, right? We see nothing in there. But there are some physical realities with this formulation. For example, when these waves, these red parts show where they actually accumulate up, where there's a ton of these waves. So when these waves accumulate, things emerge. And these are called quarks. That is really one of the most fundamental particles of our universe that makes up the protons, the neutrons. And then eventually it makes up the atoms, the molecules, and then us. So we are all made of quarks. And these things, these waves that bump into each other and fluctuate and accumulate, and to a certain extent that there will be something that appears. So that is very strange, and it says the vacuum is perhaps not as empty as we thought it was. It wasn't, we thought it was empty, we thought there was nothing inside, but now we see there's something inside. So how can we deal with this situation? We are again at this very interesting position where there's something new, and that's what we discovered. And if this entire theory sounds a little bit bizarre, this is crazy. How can we be made of waves? You and me, we are flesh and bone. We are made of particles or whatnot, atoms and all of those. This is actually the most accurate theory we have to represent reality, the most accurate. And just to show how accurate it is, let me show you an example. So this is the G value. And you don't need to understand what the G value actually means. It relates to something about the electron's magnetic properties. So up there is our theoretical prediction of G. Down here is the experimental value of it. And you can see the two matches up perfectly to about 12 digits. And that is 1 in a billion of a deviation. And that is a very, very small deviation. And you will be happy in any other subject, such as economics, if you even get the place before the decimals right? This is very accurate. But let's just give a quick recap of what we have said right now about quantum mechanics, about quantum field theory. So quantum field theory says everything is made of waves. You and me, we are all made of fluctuations in space and time. So for example, something we may call electrons, how does that emerge? Well, it's just the electron wave, and it fluctuates. in space-time, and then boom, there's an electron. So things are just fluctuations in waves, and because of this uncertainty principle, we cannot measure both the position and momentum 100% accuracy, so I cannot stand still. Right? So these waves have to fluctuate. They have to move around. They have to be very crazy about it. All right, so there we have it. But do we actually have everything? Have we understood everything? Right? This is incredibly accurate. But do we have everything? That is the question. And the question we're seemingly solving here is the how question. How particles move, how waves evolve, how big this G value is. But we're seemingly leaving out one big question that constitutes most of our intuition of the world, the why question. And for example, why we live in a three-dimensional space? Why does time only move forwards, not backwards? And these questions may seem really invaluable because after all, what is answering them going to help us? It doesn't really give us anything. And we also don't ask these questions such as why we live in a three-dimensional space, because we do live in a three-dimensional space. We are born into a three-dimensional space that gives us the intuition of everything. We are born into it. But every once in a while, you see something incredibly strange that destroys everything you understand. And that's what, for example, like the quantum mechanics. It's nothing like you've ever seen before. So now the question of why becomes incredibly important because we don't understand it. And quantum mechanics says a ton of peculiar things. It says nothing is deterministic anymore. Everything is governed by this wave function. All of us are probabilities. Nothing is deterministic anymore. And it also says that only when we observe something, like this wave. I observe you, so you exist. But that does mean that if you guys don't see me or I don't interact with any of these lights and these waves and all of these things, I don't exist. I'm not flesh and bone anymore. Now that is ridiculous, right? If you think about it, how can I just not exist if nobody sees me? And these are the questions. So now we ask, why is it that way? Why is quantum mechanics so strange? And if that sounds too distant, how can we understand this entire thing about it? Right? How can we understand that waves just fluctuate like this? And this really ties us back into the start of this talk where I said, we don't know yet. Right? The answer to this question is, we don't understand. And you also see here what we ask. When we ask about nothing, what is nothing, we don't really just ask about how these wave functions move, how these waves evolve, how quantum field theory can explain all of this thing, explain what is nothing, right? Just give us a picture of this thing and we're done. No. We have to ask ourselves, why is it that way? How to make sense of it? And in fact, just the ability to calculate is very contentful for a lot of physicists. Well, they think if we are able to predict the future, describe everything, we don't need to understand the theory. And that is very important, of course, to predict things. And that is really what physics is all about, right? We try to find a pattern, and then we try to fit it with things in the future, and we try to predict things, we try to describe things, and we try to fit everything inside these tiny equations. And that would be right? The thought that we don't need to understand what quantum mechanics means. We don't need to understand what quantum field theory means. But we don't understand everything. We don't have the ability to describe everything. In fact, there are things like quantum gravity where we try to accommodate the differences between the continuous wave functions in gravity and the discrete energies in quantum mechanics. There are dark energy, dark matters that we have not seen yet at all in our modern observatories, right? These things we don't understand. So it is, in the end, important that we do look at the why question, understand why these things work, why quantum mechanics, why this and that. Sadly, we don't at the current stage. We just don't. At the start of this talk, we encountered this idea that light can just pass through a sea of nothingness. And Einstein said, well, we don't have to worry about it. It's just the way it is. Light just passes through nothing. And there's the ether theory, who asked the direct opposite. Why can the light pass through a sea of nothingness? It shouldn't be that way. There should be a medium. And Einstein's theory was right, actually, because even with all these fluctuations, even with all these quarks and gluons, these are not mediums for light. Light don't travel in these things because they're not light particles, right? They're just other particles moving in and out of existence. So there is no medium for light. But does that mean that the ether theory doesn't work out? Well, it actually turns out that it is only because we ask the whys that we do understand so much about quantum mechanics, that we do understand so much about quantum field theory today. It is particular because we asked why. And although we didn't get the exact answer we were hoping for, right, the medium theory, we didn't get that. But we get some other astonishing things that were really great as well. And perhaps it can be said about the same thing to our current dilemma, how we can figure out this strange thing about quantum field theory and quantum mechanics, how we can make sense of that. It's only when we make our first step to ask these questions and to understand that we do not actually understand them, can there be progress. And that is really what I want to share with you today in this talk. And I'll just end this entire thing with a little story that I heard or read from this famous physicist named Richard Feynman, where he explained to his students what the nature of subtraction is. So imagine a few thousand years ago, there were two Mayans who wanted to learn how to subtract numbers. And they go to find their priest. The priest says, well, subtraction is very easy. You just take a jar out, and then you count, for example, if you want to do 533 minus 285, you just first count 583 beans, and then put all those beans inside a jar. And then you take out 285 beans. The remaining amount of beans is your answer. Now, there is no way that we can actually do, for example, 1 million minus 1 million using this method. But that's not the point. The point is that at the end of the day, after all the fancy tricks, counting beans outside of the jar is what subtraction really is. And that is what people hope we can do the same for complexities and complex things such as quantum field theory, all those things that are extremely complex, that give us extremely sophisticated equations and predictions, to just look back, turn our heads at some point and look back and ask the question, well, what does it all actually mean? What is all of this? And that is all I have for you today. Thank you.